SAT 22 for the week of 19. Let's take a look at our problem. A small business owner budgets $2,200 to purchase candles. The owner must purchase a minimum of 200 candles to maintain the discounted pricing. If the owner pays $4.90 per candle to purchase small candles and $11.60 per candle to purchase large candles, what is the maximum number of large candles the owner can purchase to stay within the budget and maintain the discounted pricing? Well, how did we do on this question? As you can probably imagine, with a student-produced response type question, the results were all over the place. They ranged from a lowly 10 all the way up here to 10,000. That's what that 10 dot 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 is. And looking at the data, there's a clear spike here at 182 with 65% of us saying that that's what our correct answer was. And it, in fact, is the correct answer. And there's nothing anywhere close. Second place here with 10.6%, 13 people saying it was 189. And we'll get to the bottom of why that was a second popular question, or answer, I should say. Okay, and then overall, we said it was the usual level 3 medium style question. All right, so let's go ahead and dive into the solution. And the solution to this is an example of what is called linear programming or linear optimization. And that's assuming that you didn't do it by guessing and checking, which probably most of you did. Program, I think there's two M's in that. And linear programming, don't let the terminology fool you. It has nothing to do with writing a program, either on a calculator or a computer or anything like that. It has to do with linear inequalities that define some kind of problem situation, like the one that we have here, with a variety of constraints. Like, for example, we have this budget here. And whenever you graph a linear inequality, remember, let's say I have myself a line here, and then we usually shade a portion of the plane. It's called a half plane. So maybe this one gets shaded down below, all right? And then I have some other constraints that I have to take into account. And maybe that's this red line here. And maybe for this one, I'm going to shade above the line. And then the solution to this system of linear inequalities, of course, is the overlapping region. And the overlapping region has an infinite number of solutions. And you're tasked with finding, hey, what's the best possible solution? Now you have to define what best means. Best could be, let's say, for example, the largest number of large candles, or it could be something else. Maybe you want to minimize something. So when we do this thing called optimization, we're finding the biggest of something possible or the smallest of something. It could be about money, it could be about area, it could be about volume, and in this case, it's going to be about the number of candles that we're talking about. And so where on here, on this kind of graph situation, would we find the best or most optimum solution? And those solutions occur at the boundary points, at the vertices of the polygon that's formed by the overlapping region. And you'll see that whenever we graph all of the inequalities that define this situation. But first, of course, we got to come up with some inequalities. So let's take a look at our numbers here. So the first number is the 2,200. That is our budget. We can't exceed that amount. If we exceed that amount, I don't know if we go out of business, we get fired or something, I don't know, but that's the amount that they allocated for candles. And so I'm going to just write something simple like our cost has to be less than or equal to $2,200. In other words, it's totally okay to spend the full budget, and it's really okay to spend less than that, but you can't spend over that. As a matter of fact, I think a lot of people stopped right about here. Actually, maybe didn't even write an inequality down. Just started plugging things into the calculator, started dividing. So for example, what if we spent all of our money on the large candles? Would that give us the maximum number of candles, large candles, that we could buy by taking this 2,200 and divided by $11.60? Let's see what happens when we do that. So if I take my 11, no, got to start with a budget. 2,200 divided by 11, divide by 0. You're not supposed to. 11.6. And look, there's that number that we saw on the chart of everybody's answers, 189. There's also some decimals attached to it, 189.655. We look back at our bar graph over here, and you can see that those were some of the answers. So you can see right here, 189.6. The little spike right there with 10.6 was actually 189. And then there were some people that rounded down. There were some people that rounded up. And you do have to do a little bit of rounding here because, well, you can't buy a fractional number of candles. At least I don't think you can. But there's a problem with 189 or even 189.6. And the problem is you haven't reached the magic number of 200 candles. Remember that in order to lock in that discount price of $11.60 per candle, you have to actually have 200 candles. And we're not when it's 189. So that's another inequality right here. The number of candles has to be greater than or equal to 200. If it's 199 or 189, you haven't bought enough candles to actually meet the minimum requirement. So probably people that were successful at getting 182 candles started fiddling with their numbers, doing a little bit of guessing and checking, maybe decreasing this 189 and then increasing correspondingly the number of small candles, and then figuring out what the cost total is going to be, which you can totally do. Guessing and checking is a viable solution or a viable strategy in a lot of situations, but sometimes it actually takes longer to do that than a more, let's say, rigorous approach, which is what I'm going to show you. It's going to take out all of the guessing, all of the guesswork, and get straight to that solution. And you might look at the solution that we're about to do here and go, well, I think I could have guessed and checked that a little bit faster. And I'm not going to argue with you specifically, but if you know exactly what the process is here, it's pretty fast to set up your inequalities, throw them into Desmos, and then quickly find your solution, as you're about to see. So in order to actually get this graph picture here, we need some variables. And the variables, there's two of them, because we're wanting to know how many small candles we can have, and then also the large candles. And the large candles, of course, are the ones that we're trying to maximize. So I have both the small and the large. Those are going to be our two variables. We can just call them X and Y. X, let that be the number of small candles, and let Y equal the number of large candles. And I think there should be an L in there or something. Canned, except for I spelled it wrong. L-E-S. There we go. All fixed. I just did a spell check on there. Anyway, so I'm going to use this information to write ourselves some inequalities. And the first easiest one is using these three pieces of information here. The total number of candles, which is our small candles plus our large candles, has to be more than or equal to 200 in order to get the discount. So I've got X plus Y has to be greater than or equal to 200. So let's go ahead and just graph that on Desmos. X plus Y greater than or equal to 200. And you see the graph completely disappeared because it's way, way up here in outer space, because it has a y-intercept of 200 and then also an x-intercept of 200. Okay, so an inequality, the line itself, since it is equal, any point that's on the line would satisfy that inequality. You would have a total of 200, exactly 200 candles. And the shaded region that's up above it, any point there would be when you had more than 200 candles, which is something that you can totally do. Okay, so that's too many candles. We need to be able to narrow it down with another inequality. So let's take a look at our problem. And then let's make ourselves a cost equation where our cost, our budget, cannot exceed 2,200. And that 2,200 is coming from how much we're spending on small candles and how much we're spending on the large candles. To get the amount of money that we're spending on small candles, we would take its cost, 4.9, and multiply it times X, the number of small candles. So 4.9X plus, and do the same thing for the large candles. Take its price and multiply it times the number that we're buying, so 11.6y, and that has to be less than or equal to 2,200. And there we go. Let's throw that into decimals, graph it up with the other one, and see what happens. 4.9 x's plus 11.6 y's. That has to be less than or equal to 2200. There we go. And so our solution here is actually, let me change some colors here if I can. I think I can. Let's change it to some kind of color theory going on here. So our solution is the purpley thing, the overlapping region. It's not just, say, the red stuff, not just, say, the blue stuff. It's where they overlap in the purple region. Now, we would discount anything that is down below the x-axis, because if you're below the x-axis, that means your y is negative. And if your y is negative, that means you bought a negative number of large candles. And I guess the company you're buying them from owes you some candles? I don't know. So what we were saying about this linear programming aspect of this is where we find the optimum number of solutions, right? This triangle, this purple triangle, has lots and lots of solutions in it. But the optimum solution for a given situation is going to occur at the vertices. And there's 3 vertices that we can look at. And you don't know immediately which one it is until you test something out. So let's take a look at this one. And remember that we're trying to maximize y. We want the biggest y value. Anyway, so let me take this number and then just put it into the table over here. And the x value, the 17.9, is supposed to be the number of small candles, and then the 182 is the number of large candles. And of course, we'll have to do a little bit of rounding because you can't buy, like we said, a decimal number of candles. Is that the solution? Or should it be one of these other 2 points, like, for example, the 200, 0? No, it can't be that one, because that means that you bought no large candles whatsoever. I can already see from the previous point up here that we can buy more than 0 large candles. And then likewise, I would eliminate this other point, this third point of the triangle, for the exact same reason. Let me pull this thing in. Here, this implies that you spent your whole entire budget on small candles and you bought no large candles at all. No, nobody wants that situation. So you would you would eliminate these 2 answers. And the most sensible answer is the one that we have highlighted right here. Okay, and then we'll have to figure out what some rounding is, because, well, we've already mentioned about 1,000 times we have to get rid of the decimals. We got to buy a whole number of candles. So we might think that we're going to take that 17.9 and say that we're going to buy 18 of the small candles plus, and then round the 182 point whatever to, well, it looks like it rounds down to 182 candles. And look at that. We have our magic number of 200 candles. So we've met the minimum requirement in order to qualify for the discount. So now let's check to make sure that we have the correct cost. So if we take the 18 small candles and multiply it times their cost, 4.9, and then add in the 182, right? And then multiply times their cost of 11.6, you can see that we're just under the $2,200 threshold for our budget. We actually saved ourselves 60 cents. Now, is there a better solution than this? Well, you might go, well, can I get one more of these large candles? Here, let's delete out this 2, make it a 3. Oh, we just went over budget by 11 bucks. Okay, so that just means that I need to subtract away one of these small candles, make that 17. Oh, I'm still over budget. Okay, so then I need to subtract away another one. But none of that is necessary because we already found the optimum solution. And the optimum solution in this case was the biggest y value. And you can see it's the highest point in the region, which represents all the possible solutions anyway. So we've reached our answer of y is equal to, being the large number of candles, 182 large candles. And then just, type this into the form and be done with it. But are we done with it? No, because there's always somebody who asks, is it possible to do this with, like, without using decimals, without graphing it? And you can, but I'm going to tell you, it is so extra. What I mean by that is that you would probably spend more time doing that part of the solution, the algebraic solution, then you should spend on any one question. But I'll show you anyway because it's kind of interesting, and it's based around the transitive property, which we are intimately familiar with, transitive property. Now, the transitive property, as we've seen it, has to do with equations of stuff. Also, syllogism with conditional statements. But the transitive property, as we know it, is if A is equal to B and B is equal to C, then A is equal to C. But it also applies to inequalities, and it could be either the greater than or the less than. We're going to use the less than. So A, write it conditionally. If A is less than B and B is less than C, well, what do you think? Doesn't that imply that A is also less than C? And that is the transitive property for inequalities. So what we would have to do if we're going to do this algebraically by hand is that we would have to try to make, in this case, this B match up with this B. We have two inequalities right here. We have to make both of them have something in common, which is the B side, whatever this B thing happens to be. Also notice this. Notice that the inequalities are all facing the same direction. They have to continue to face the same direction. So what I'm going to do is I'm going to take this top equation and just flip it over, which you can totally do. So I'm going to duplicate this real quick. Boop. And I'm going to take that top equation and then flip it over. And pay attention to, like whenever you flip an inequality, you have to also flip the inequality sign. So I'm going to have 200 on the left-hand side is less than or equal to x plus y. And now from like a third grade, fourth grade, fifth grade perspective here, thinking of the alligator mouth munching on the x plus y, it's continuing to munch on the x plus y, so we set it up correctly. Okay, so does this x plus y look like this? No. Does this look like? No, it doesn't. So what we have to do is some algebraic trickery, some manipulation to make them match up. And so here's what I'm going to suggest that we do. Now we can do this either with the x or the y. I'm going to choose the x. I'm going to subtract the y over to the left-hand side of this equation. So we just focus on one of these variables at a time. I got 200 minus the y is less than or equal to x. Okay, so now I have just one x over here, but the thing that I'm trying to match it up with right here has 4.9 x's. Well, how do I make my 1x actually be 4.9 x's? Well, that's pretty easy. All you got to do is multiply both sides by 4.9, which you can totally do with either an equation or an inequality. The only thing you have to watch out for when you multiply both sides by a number when you have an inequality is if it's negative, you have to flip over the sign, but ours isn't, so we're good to go. So let's multiply everything by 4.9. 200 times 4.9 is, let's divide. 4.9 is an exact 980. Minus, now the y also needs to be multiplied by 4.9, is less than or equal to, of course, 4.9 x's. All right, we are part of the way there. The 4.9 x's match up with this 4.9 x's. Oh, but I'm missing my 11.6 y. And now I don't want to try to make this that I added to the left-hand side of this negative 4.9y into the 11.6y. I'm going to do it differently. The way that I'm going to get my 11.6y over here on the right-hand side is that I'm going to add 11.6y to both sides. Is that a legal move? Sure, you're allowed to totally add the same quantity to both sides of an equation or an inequality, and it's still balanced. So 11.6y, add that to both sides of this inequality, and watch what's about to happen. Okay, so on the left-hand side, I still have my 980, bring that down. And then I have to combine these two y's together. They are like terms. And it's going to end up being positive something. I think it's somewhere around 6. 11.6 minus 4.9, 6.7 plus 6.7 y's is less than or equal to, now on the right hand side when I combine these, they're not like terms, so you just list them out. 4.9x plus 11.6y. Can you see what I'm saying? That this is kind of extra in this case? Right. Anyway, some of you are probably saying, well, it was extra for me to actually even come up with these inequalities and graph them. But I disagree. Anyway, so now we're pretty much good to go. And I will show you that by coloring some stuff for you. Who doesn't like coloring stuff? So my A value here is going to be my 980 plus 6.7y. My B, which I already highlighted in blue, is going to be the 4.9x plus 11.6y because it's the thing that matches up on both of these inequalities. And then everything is going to be less than the C value, which I'll highlight here in red, and that's going to be your 2,200. And I can actually combine these in a compound inequality, and we usually write these things from smallest to biggest. So the smallest side is the thing that's in green here. That's your 980 plus 6.7y, which is less than or equal to the blue thing, 4.9x plus 11.6y, which is less than or equal to the red thing at 2,200. Now, using the transitive property right up here, we get rid of the b. We get rid of the middleman, and we go straight from the first one, the smallest thing, to the last thing, the biggest one, c. And so your new inequality becomes 980 plus 6.7y is less than or equal to 2200. And now you have an inequality in just one variable, and we can easily isolate that y. And y is the thing that we're trying to find anyway. So to isolate the y, get rid of the 980 first, so we'll subtract that to the other side. So 2,200 minus 980, we get 1220. 6.7y is less than or equal to 1220. And then finally, I'll just divide both sides by 6.7. 1220 divided by 6.7. Hey, that number looks familiar. 182 point decibels. As a matter of fact, it looks exactly like this point over here that we labeled as that point of intersection. Actually, ours is just a teensy bit more accurate. And this all goes to show you that we could have avoided all of that work by just graphing those inequalities and finding that vertex point, which maximizes the number of large candles. But this does show you that you can do it algebraically if you've got the time, but you certainly wouldn't have the time on the actual test, though. So that should do it. That should conclude the video on how to maximize the number of candles, in this case, via linear programming.